Now let's start with a simple example. Let's start with the function defined on 0, 1. Under the usual metric, this actually is the most famous compact set in R, with values in R. Let's define it as 1 over x if x is different than 0, and 0 if x is equal to 0. Now, if we have its graph, this is 0, this is 1. Now, it takes on the value here, but as we approach 0 from within this set, then 1 over x, that actually increases without any limit. So it is just this, and at 1, it's 1. So it's something like this. This clearly has no maximum. Maximum of f of 0, 1 does not exist. Although the set 0, 1 is compact with respect to D. Now here, the non-smooth behavior is, well, as we come closer to 0, the value of x, the value of f at x, well, that does not get closer to its value at 0. In fact, it goes farther and farther away from that. So for smoothness of a function, descriptively, roughly, intuitively, well, we can say, well, if both the domain and range, they have a topological structure, close points in the domain should be mapped on close points in the range. Whatever that means. Well, in general, in a topological space, closeness is described via the notion of what? A neighborhood. Well, if we have a neighborhood V of the image of f under x, f of x, well, we can talk of cap V closeness of a point to f of x, or in the range as well. U, a neighborhood of x, well, we can refer to points in that neighborhood cap U as U close points to x, okay? Okay, now, well, we'll do that. But here we also have some other small problem that we have to deal with. Now, 0, 1, that's a subset of R. But I said, well, that's a metric on R. Of course, if we consider this as our space, then we naturally think of as a relativization of the metric on R to this smaller set. And here, if we talk of points close to 0, well, in R, they could be on both sides of 0. But if we confine ourselves in here, they all have to be in this set plus being close to 0. So, for example, given epsilon positive, here the set of all epsilon close points to here, they are the set of all points in 0, 1, such that dx0 is less than epsilon. Here that is, if we write it as an interval, it's this interval. Now this automatically assumes, we will now formalize that, well, if we have a metric space, cap x rho, then a non-empty subset cap A of x, since rho is a function on cap x cross cap x with real values, well, we can restrict that to cap A cross cap A. The restriction, but that will turn out clearly to be metric on cap A. Now let me first write that down. Now let x rho be a metric space, and let us take a non-empty subset A of x. We define rho sub, well, let me write it like this, rho sub A as the restriction of rho to A cross A, because rho is on x cross x, A cross A is a subset of that. Check that. Rho sub A is a metric on A. Now we refer to A rho sub A as a, well, we usually delete the metric part as a metric subspace of x rho, and also we write for this simply A rho instead of A rho sub A. That's just an abbreviation, a simplification of notation. Well, that's fine. But here, in defining a subspace, A rho, well, we took advantage that rho was a function, and we took this restriction. But what can we do if we wish to formalize a similar subspace structure for general topological spaces, that we do not have any function metric which we can confine, restrict to a subset? But there we can make the following observation. Well, we can write this as also, we can take the epsilon ball d about 0 in R, so that will be minus epsilon to plus epsilon, and take its intersection with 0, 1. In fact, any epsilon ball in this subspace can be written as an epsilon ball in the large space R, which is intersected with this set. So, taking intersections, that we can do in the general topological space context as well. Now let's go through a similar structure here, but this time in general topological spaces. So we'll start with a topological space, and we'll take a non-empty subset A of X. The question is to define now, to derive now a topology on cap A from the topology on cap X. Set tau sub A equal to, well, if we take this as our motivation, we'll take open sets in cap X with respect to tau and intersect them with A, where G is in tau. Now it is straightforward to check that tau sub A is a topology on cap A. Check that. Tau sub A is a topology on A. Now, we refer to A tau sub A as a, well, we again usually express this topological part, since it's self-understood, as a topological subspace of X tau. And as over in that case, we write for this simply just A tau. Having A in here, that will automatically mean that tau has been relativized with respect to that set. Okay? A simple proposition. Well, open sets here are intersections of cap A with open sets in the larger space. What about closed sets? Well, once this is a topology, a subset of cap A, that will be closed if its complement is open, that is, belongs to tau sub A. But you can easily see that also will turn out to be the intersection of cap A with some closed set in the large space. Proposition. Now, let us take this. And let C be a subset of A. Now, C is closed with respect to, well, let me write it closed in A with respect to tau sub A if and only if C is equal to A intersection B for some subset B of X, which is closed with respect to tau. Now, proof is simple, so that's left to you. Here, we also use the following terminology: G open relative to cap A with respect to tau, or C closed relative to A with respect to tau. This is an open set in tau sub A, a set belonging to tau sub A, and this is a closed set in this topological space, but we use this notation as well. Now let's first have a break, and then next hour we'll start with the formalization. If we start with the metric space, one way is to first find the topology it induces and then relativize that topological space with respect to a subset. But we can also proceed the other way around. We can first relativize the metric with respect to a subset and then consider the topology it induces. Now, if they turned out to be different, that would be something that we would not like, but fortunately, they turn out to be equal to each other. Now, let me write that as a proposition. Let X rho be a metric space and A a subset of X. Now, rho sub A, that's symmetric on cap A, and it induces, now let me write it like this, the topology here. Okay? But on the other hand, we can consider the topology induced by rho, then relativize this topology with respect to cap A. These will be equal to each other. Well, again, the proof is simple, so it's left to you. A small example. Consider RD as the space that we start with. Well, first consider A to be 0, 1. Now, if you consider 0, 1 half, 1 half excluded, if you consider this in the big space, this will be neither open nor closed. This is neither open nor closed in R with respect to D. But on the other hand, with respect to cap A, we can write this as this open interval. That will be open with respect to tau D, with respect to the topology this induces on R, intersection 0, 1, which is A. But this now is, according to our definition, open relative to cap A with respect to D. Is open relative to cap A with respect to D. Okay? This is open in the subtopology, or this is open with respect to the submetric. Let's consider something which also involves closeness relative to a subset. Now let us take A instead of 0, 1. The set of rational numbers. And let us consider the set square root of 2 square root of 2 plus 1 intersection Q. Is it closed relative to Q with respect to D? Well, is this set closed in R with respect to D? Yes. Well, this is the intersection of Q with a set which is closed in the big space. Thus, according to our proposition, this is closed relative to Q with respect to D. Is it open relative to Q with respect to D as well? Well, since square root of 2 and square root of 2 plus 1 do not belong to Q, this is simultaneously equal to square root of 2 plus 1, this open interval intersection Q. But now it's an open interval, an open set in the large space in R with respect to D, intersected with Q, is also open relative to Q with respect to D. So in the subspace, where the space is restricted from R to Q, to rationals, well, this set is both open and closed. Now let's define continuity. After this preparation, let's define it in the general case. Let x tau and y tau prime be topological spaces f on x to y, a function, and a point in X. Now we say that F is continuous at A if, well, the pictorial rough, the intuitive description was close points to A in the domain should be mapped onto points which are close to f of A in the range. But then we need a measure of closeness for f of A and for A as well. But in topological spaces, we have introduced the notion of a neighborhood for that purpose. So if for every neighborhood V, of f of A, of course, with respect to tau prime, let me write that at least in the definition. So you give first the measure of closeness in the range, closeness to f of A, that's represented by f of V. There is some neighborhood U of A, this of course with respect to tau, such that f of u, which is just the set of all f of x, x in u, is contained in V. So if x is u close to A, then f of x should be V close to f of A. So that's what this says. For any non-empty subset A of x, we say that f is continuous on A if f is continuous at each point x in A. When we usually define a real valued function, for example, on a subset of R, not on the entire R. Well, if that's the case, we consider the domain with respect to its relative topology. Well, let me write that in general, that convention. Now that x tau, y tau prime be topological spaces A, a non-empty subset of x, B, a non-empty subset of y, and f on A to B a function. When we talk of continuity of this function at a point in cap A or on a subset of cap A, then we mean it with respect to the relative topology here as well as the relative topology here. Continuity of f is to be considered in terms of A tau sub A and B tau prime sub B. Okay? So that's just the convention. Next. Let us try to introduce equivalent yardsticks to continuity, which might usually be easier to check rather than resorting going back to the definition itself each time. But we will do that in two different contexts. One will be in metric spaces and local properties, that is, continuity at a point. Then we'll consider that in the context of general topological spaces, but that will be global continuity, continuity on the entire domain. So the first theorem local properties of continuous functions in metric spaces. So we need let X rho, Y rho prime be matrix spaces, and let us take just X in cap X. Now the following are equivalent. The first is F out. That, of course, we need a function. Let xy be a function. Now f is continuous at x. Or let me write a here. Let me use x for the generic element, continuous at a. Secondly, well, we have the famous epsilon delta definition in calculus. For every epsilon positive, there is some delta positive, this depending upon, in general, what this epsilon is, such that here, this gives us a measure of closeness in the range space to f of a, and this gives us a measure of closeness in the domain to the point A, so such that points which are delta close to A with respect to rho are mapped upon points which are epsilon close to f of a with respect to rho prime. If you take any point in this delta ball about A, that's delta close to A with respect to rho. If you take the image of that, f of x, well, that should be in here. Well, that means f of x and f of a, according to rho prime, should be closer to each other than epsilon. Okay? Here, this u is replaced by delta, and this v, that's replaced by epsilon. Thirdly, now we introduced sequences as a simplifying tool in metric spaces. So every metric property has a sequential version. Continuity does as well. For any sequence, xn in X with xn converging to A. This, of course, with respect to rho, one has that f of xn converges to f of A, and this with respect to rho prime. Well, since we are to show that these three are equivalent, well, the shortest way is to go in a triangular way. We will prove that 1 implies 2, 2 implies 3, and 3 implies 1. Well, 2 implies 3. That will be left as an exercise to you, but we'll prove the rest. So proof, the first is 1 implies 2. So we'll start here by assuming that 1 holds. Assume that f is continuous at A. To show that then this holds, we should start by taking any positive number epsilon and then produce some delta such that this holds. So take any epsilon positive. But now the definition is in terms of neighborhoods. But can we associate with epsilon some neighborhood of f of A with respect to rho prime? Yes, this is an epsilon ball about f of A with respect to rho prime. That's a neighborhood of f of A with respect to the topology induced by rho prime. Now, we know that, so let me not write that part. B rho prime epsilon f of A is a neighborhood of f of A with respect to rho prime. But by definition of continuity of f at A, in response to this given neighborhood, there is some neighborhood U of A in the domain such that f of U is contained entirely within this set. So since f is continuous at A, there is some neighborhood U of A with points which are U close to A are mapped onto points which are in here, that is, which are close to f of A, epsilon close, with f of U being contained in B rho prime epsilon f of A. The question is now, in order to complete that this statement holds, whether we can produce some delta ball about A with respect to rho, which entirely stays within U. But what's the definition of a neighborhood in a topological space? Now there should first exist some open set which contains A and which is contained in U for U to be neighborhood of A. Now, there is some open set G, this with respect to rho, such that A is in G and that's contained in U by definition of a neighborhood. But we're in a metric space, G is open and A is in there. What do we know? Well, there must be some delta ball. Since we used epsilon elsewhere, there must be some delta ball about A, which is entirely contained in G. Since G is open, there is some delta positive such that the delta ball about A is entirely in G. But this is in U. So F of this set is contained in F of this set, but F of cap U is contained in here. So f of the delta ball about A with respect to rho, that's contained in f of u, but that's contained in the epsilon ball about f of A with respect to rho prime. So given any epsilon positive, we have produced some delta positive such that the image of the delta ball about A, that's contained in the set in the epsilon ball about f of A, well, with respect to rho and rho prime respectively. Okay? Here, the whole idea is, well, epsilon balls are neighborhoods in metric spaces. Something given in terms of neighborhoods that's translated to something in terms of epsilon balls in the metric space. 2 implies 3. That's left to you. Now let's show 3 implies 1. Any questions so far? Now assume that 3 holds. To show that then 1 holds, let's proceed by contradiction. Let us suppose that although 3 holds, f is not continuous at A. Well, then, to reach a contradiction, well, we should attempt to construct a sequence in cap X which converges to A, but f of xn does not converge to f of A. But once we observe that, it is almost clear how to proceed. But suppose one does hold, that is, suppose f is not continuous at A. Well, let's spell out in detail what this means in terms of the definition. For continuity, for every neighborhood phi of f of A, there should exist some neighborhood u of A such that f of u is contained in V. The negation of that is that there is some neighborhood V of f of A such that no matter what neighborhood u of A you take in the domain, f of u will not be contained in V. Then there is some neighborhood V of f of A such that for any neighborhood u of A, f of u is not contained in V. Now let's use this to construct an appropriate sequence xn, which converges to A, but the sequence of the images under f of xn, that does not converge to f of A. Now, if something is true for any neighborhood u, And if we wish to construct a sequence, then we take a sequence of neighborhoods. Well, 1 over n balls about the point whose neighborhood we talk of. Now, for each n in n, B rho 1 over n of A is a neighborhood of A. Well, this says no matter what n I take, f of this 1 over n ball about A, that will not be contained in V. Now, for each n in n, f of 1 over n ball about A is not contained in V. But this means this 1 over n ball about A with respect to rho that contains a point, say x sub n will depend upon n, such that f of xn is not in here. So, for each n in n, there is some x sub n in such that f of x sub n is not in V. This is simply, well, or rather, this last statement is just what this means. But what can I tell about x sub n's? Well, as n gets larger, the distance of x sub n to A, that actually gets arbitrarily small. So, well, let me write that, check that. X sub n converges to A. What can I tell about f of x sub n? Can it converge to f of A? By definition of convergence, for every neighborhood of f of A, there should be a slot in the sequence such that from that point on, the entire tail would belong to that neighborhood. Well, is there some neighborhood of f of A where this does not happen? It's V. In fact, none of the terms of the sequence belongs to V. So, as V is a neighborhood of f of A, and for all n in n, f of x sub n is not in V, we conclude that f of x sub n does not converge to f of A in contradiction with 3. Because we assume that 3 holds, x sub n converges to A, that should imply that f of xn converges to A as well, contradicting 3. Well, or in contradiction with 3. So, this supposition must be false. F is continuous at A. Now let's consider an example to see how useful these two characterizations are. But let me ask the following question. In calculus, well, let's consider real-valued functions of a real variable. They're defined on R with real values. If I give you a finite non-empty set in R, to construct a function which is discontinuous at those finitely many prescribed points, that's no problem. But if I asked the converse, given a finite set of points in R, they have to be discrete, they're finite, can you construct a function which is continuous at those finitely many points, but discontinuous everywhere? To be more specific, let me give just one point. A singleton set is finite. 1 point in R. To be even more specific, well, let that point be, say, 1/2. Does there exist a function which is continuous at 1/2, but not continuous anywhere else in R? Do you think that there are such functions? It's difficult to imagine a picture, the graph of such a function, but that's true for any non-empty finite set. In fact, we'll do it now for 1 point where x is equal to 1/2, but how to extend that to finitely many points, that will be clear from the example itself. For that, rationals and irrationals, they're of course important. Now we define it as follows. We take it as x if x is irrational, and we take it as 1 minus x if x is rational. Now we can first look at the graph. Now, well, fx equal to x, if that were for all reals, the graph of that would be this. What about fx equal to 1 minus x, if that were for all real numbers? Now that would pass through these points, 1, 1 here, it would be this. The graph of this function is if x is irrational, then you take it as this, its value, this point on the graph. But if x is rational, then you take the graph on this line. Now here, at 1/2, that's rational. So here you have 1/2. But this function would take on the same value. So what we expect is that this will be continuous at 1/2. But no matter what other point we take, depending upon whether this is rational or irrational. In case of irrational, the point on the graph will be this. In case rational, the point on the graph will be the other. But there will be a positive distance between these two. And whatever neighborhood of this point I take, it will contain both rational and irrational points. Thus, the image of each point under F can neither be close to this all the time, nor close to this all the time. Well, if this is the graph, well, then there will be points in here. If this is on the graph, then there will be points on here. That's what we'll use, but let's go through the details as well. Well, we will not be able to complete that today, but let's do it up to some point. Now, first consider x equal to 1/2. Well, or 1/2. Or let me write it as claim. F is continuous at 1/2. Well, let's use this epsilon delta version. Proof. Let epsilon be given. But these are both straight lines, well, with slope 1 and with slope -1. So what delta would do here? Well, if I were just to show that y equals x is continuous everywhere, then epsilon equal to delta would do the job. Because if this is, well, I would have just this square, and if x is in this neighborhood, then f of x would be in this neighborhood. Well, the same would be here, but since they coincide here, set delta equal to epsilon. Take any x in the 1/2 ball, in the delta ball about 1/2 with respect to d. Now, we're interested in f of x minus f of 1/2. So this is the usual distance. We're using the usual distance. But f of x, that will be x minus, and f of 1/2, that's 1/2 minus 1/2, that's 1/2. This will be x minus 1/2 if x is irrational. Because if x is irrational, f of x will be x, f of 1/2 will be 1/2. And this will be, if x is rational, this will be 1 minus x minus 1/2, but these are the same. This is 1/2 minus x, the absolute value, 1/2 minus x. So they both, in either case, will have that this is equal to x minus 1/2. But since x is in here, this will be less than delta, but delta is equal to epsilon. So f of x here, for all x in b delta 1/2, we'll have that f of x is in the epsilon ball about f of 1/2. Hence, f is continuous at 1/2. Well, we'll continue with this example on Thursday by showing that it's not continuous, it's discontinuous everywhere else. Just what we'll do is what we have seen, what we have observed on the picture, we will just formalize that.